Good morning, everyone. For the next few lectures, actually, we're going to depart a little bit from what we've been doing for quite a while. We've been studying a lot of structural complexity, the theory of complexity classes and so forth. And we're going to spend a few lectures on an area called concrete complexity, which is, really about proving like explicit combinatorial lower bounds for simple, explicit models like circuits and things even weaker than that, as opposed to these higher level things of languages and running times and so forth. So, the dream in this world is, of course, to show not just p does not equal np, but maybe even np is not contained in p/poly. So SAT, cannot be computed by polynomial-sized circuits. Well, that's the dream. Of course, it's very, very hard and unobtainable, potentially. So people have, said, let's scale back our ambitions, or other way to think about it is, let's start from easier cases and maybe work our way up to p/poly. So, one aspect of this program is to say, okay, instead of, general polynomial-sized circuit families, maybe we can try to prove lower bounds against simpler classes of circuit families. Okay, so, I look at, let's say, weak circuit models and try to show that, SAT or some other languages in NP cannot be computed by, very weak circuit models. And then maybe if you eliminate the restrictions enough, you can build up to p/poly. The funny thing is that we have some success in doing this, proving lower bounds for weak circuit models. But it's slightly embarrassing to admit, the way that eventually works is that you'll even show that p is not contained in these weak circuit models. So you have to ask yourself, well, is it, do we show, do we really not show that, there's something hard about SAT? Maybe we just showed there's something really weak about these weak circuit models. But, anyway, we do the best we can, and that's what we're going to start with today. So today we're going to talk about these guys, AC0, meaning constant depth circuits. Well, you got to start somewhere. And in some sense, it starts and ends with constant depth circuits. We know a little bit lower bounds against slightly stronger models, but that's that. These are sometimes, I'll remind you, called AC0. So AC0 refers to the class of all languages that have poly-sized constant depth circuits. But I won't necessarily fixate on polynomial size because we'll actually eventually show things require exponential size AC0 circuits. So I might accidentally say AC0 when I really just mean constant depth circuits of potentially any size. So good. So what do constant depth circuits look like? They look like this. Now this is actually not the most general looking circuit, but circuits basically without loss of generality look at like this. So what do I mean by that? First of all, we have a depth here. The depth is the longest leaf to root path. So this particular guy has depth 3. And of course, since we have constant depth circuits, we need to allow our AND and OR gates to have unbounded fan-in to make it fair. So that's what we've done. And we also generally just assume that all the NOT gates are pushed to the bottom by De Morgan's laws. You can do that at the expense of at most doubling the size of the circuit. So we just do that and don't worry about it. So in fact, we therefore just think of having access to the inputs plus the negations of the inputs at the bottom level. In fact, we don't even really charge for the NOT gates. Okay, so we just charge for the AND and OR gates. So therefore, the size of such a circuit, usually denoted capital S, is the number of AND and OR gates. And there's going to be one more parameter that's quite important for this lecture and the subsequent lecture, which is sometimes called the width. But it's maybe more accurate to call it the maximum bottom fan-in. Okay, so it's going to turn out that this is quite important. The maximum fan-in of these guys, any one of these guys, and we'll call that W. Okay. Of course, it's at most N in general, but we're going to think about potentially smaller cases. Oh, finally, constant depth circuits also have this property when you have the unbounded fan-in gates that you can merge consecutive OR gates. If you have an OR gate and also AND gates, and it feeds into another OR gate, well, then you can just delete this gate and have all these wires go like this. So for that reason, we assume that like the gate, you can assume that the circuit is like leveled, like alternates between AND gates, OR gates, AND gates, OR gates. Yeah, or you can put in like dummy gates if you need to, so it doesn't change the size of the circuit much.
Is there like a restriction for using NOT gates?
Yes, I mean, if you're not concerned about like, the difference between a factor 2 in size, you can use De Morgan's laws to like push all the NOT gates to the bottom. And so we're just going to assume you always do that. And therefore, even we're just going to think of having access to the input bits and their negations. OK, so our AC0 circuits are going to look as in that picture. OK, so you might say, OK, why would we care about constant depth circuits? Well, it's part of this program of like trying to scale up from a weak circuit model to a general circuit model. You got to start somewhere. They're a model of the languages or problems that can be solved in constant parallel time, which is somewhat reasonable. It's one reasonable way to model them. The depth 2 case is a very familiar case. Depth 2 circuits are just CNFs and DNFs. So these are objects that we know and love. And as we'll see in a second, actually, even once you get to depth 3 circuits like this, they're like very concrete, like open problems about the power of depth 3 circuits that have implications for general complexity theory. OK, so as I said, we're going to actually be able to successfully prove lower bounds against this class of circuits for explicit functions. Also, as I said, this is going to be a function that's in P. In particular, it's easiest to prove lower bounds for these guys for this very simple function, the parity function on n bits, which just maps x to the sum of xi mod 2. Okay, so it's going to turn out this function is extremely hard for constant depth circuits to compute. So in some sense, constant depth circuits have a hard time counting. As I said, this is a very simple function. This problem is in P. Actually, it's in log space. Actually, it's in like space 1. It has a size 2 DFA. And yet, it's still hard for AC0 circuits. OK, so people took a crack at exactly this problem in the early 80s. And lower bounds, super polynomial lower bounds for parity against constant depth circuits were proven by Firstsax and Sipser in '83, independently by Aitai. Then like Yao got better lower bounds. But the ultimate lower bound was from Hastad in his PhD thesis in '86. And he proved the following glorious theorem that we're going to attempt to prove, or at least prove parts of. So the depth D circuits for parity require large size. And the size is exponential in n, 2 to the omega of n to the power of 1 over d minus 1. OK, so, well, I'll spell it out for you. Depth 2, this is like fully exponential. In fact, I'll show you later that it's like literally 2 to the power of n minus 1. But for depth 3, he shows that you need circuits of size 2 to the root n. For depth 4, you need circuits of size 2 to the n to the 1/3, etc. OK, this one is easy. All right, so let me make some remarks on this theorem before we dive into it. Several remarks. First of all, it's sharp. So in fact, this is, let me call it an exercise. You can compute parity on n bits in depth n, depth d, and size 2 to the order n to the 1 over d minus 1. OK, so that's pretty much the exact right bound up to the constant and the exponent. You should, in the depth 3 case, maybe break the n inputs into root n blocks of size root n. Use this strategy to compute the parities of each block. Use this strategy another time to compute the parity of the parities. Then it looks like you built a depth 4 circuit. There's a little trick you can do to squeeze out one layer, if you think about it. Good. You can also view this as giving you potential depth lower bounds for polynomial size. So you can think about it in another way. It shows that if you want poly-size circuits for computing parity, then you need depth, which is almost log n. You kind of invert the parameters, you see, you get the statement that any polynomial size circuit for computing parity must have depth that's almost log n. And this log n is kind of quite a barrier in complexity theory. We don't know how to show any explicit function requires simultaneous log n depth and linear size, even with linear size. So in fact, let me just state that. This was on homework number 2, or it was related to homework number 2. So we don't actually know any L and NP that requires. Okay, this is actually, before I get to depth, let me state this other fact. We don't know any L and NP that requires depth 3 circuits of size strictly more than 2 to the root n. Okay, so he showed that parity requires circuits, depth 3 circuits of size 2 to the root n. That's actually sharp. We actually don't know any function in NP, any explicit function that requires more than that. So for all we know, SAT could be computed by a depth 3 circuit of size 2 to the n to the 0.51. That's very unlikely, but we don't know it. And in fact, if you recall, I don't know if you can recall this far back. I had to look it up. On homework 2, question 3, if you could get, depth 3 and size 2 to the omega, I think, or maybe O, n over log n, I think it was, lower bounds. And that would imply that the same language is not in size order n and depth log n. Okay, so sufficiently strong lower bounds for depth 3 circuits are actually kind of interesting because you can translate them as you do in your homework to show that the same problem cannot be solved in sublogarithmic depth. And this is like a major challenge that we also don't know how to do. Yeah, I mean, I think it's like, I went back and forth. I think like, you'd have to show this for maybe like a sufficiently large constant. Yeah. So now you can interpret that however you like. Yeah, let me make some still further additional remarks about why this lower bound of Hastad is interesting. Another remark goes back to lecture 9, when we talked about time-space trade-offs for SAT. If you recall that lecture about time-space trade-offs for SAT, we used this kind of cute lemma, this alternation trading lemma, which showed that this fact. Any language that's in time space n and n to the little of 1, so it can be solved in linear time with sublinear space, subpolynomial space. This can be solved like even way faster in like sigma k or sigma d. So it's in sigma d time n to the basically 1 over d. Okay, so the first proofs, showed that you could simulate this in sigma 2 with like square root n time, and then for the more sophisticated ones, we use this more sophisticated result. And as I write mark, then you could ask, maybe you can just beat this and get like a stronger lower bound. But it's not hard to show that Hastad's result implies that this is unimprovable. This 1 over d can't be lowered. Basically, because computing the parity is in this class. It's easy to compute it in linear time and space 1. But like using this characterization of like sigma k time with this DC uniform like exponential size circuit business that you did a few times on the homework, you can show that this theorem actually just rules out the possibility of putting any exponent better than 1 over d here. So that's good to know. And finally, this result easily, if you're into these things, implies oracles, separations, and structural complexity. So there exists an oracle L such that P space is not contained in the polynomial time hierarchy. Okay, so you may have seen at some point this construction of an oracle that separates P from NP. And if you look at how they did that and start to generalize the technique, which is something that they're really into doing in like the early 80s, you actually find that actually constructing oracles for separating complexity classes basically just turns into the problem of proving certain kinds of circuit lower bounds, interestingly enough. So this lower bound basically immediately translates into the oracle result. And in fact, the oracle result was the initial motivation of first Sachs and Zipser for trying to prove parity is not in AC0. And in fact, the same techniques, not this exact result, but some related result about finding a problem that can be solved in depth 4 that can't be solved in polynomial size that requires exponential size for depth 3. And similarly, for any other consecutive pair of depths, you can get out of Hastad's techniques. He did it, and they imply, there exists an oracle L such that, sigma k plus 1 p to the L is not contained in sigma kp to the L. Okay, so you can separate all the levels of the polynomial time hierarchy with some oracle. And to do that, you basically need to show separation between the power of the various steps of AC0. Do you have a question? OK.
Is this L different for all k?
Yeah. Yeah, it's different from, for all k. You can probably, I'm sure you can cook one up like one L that separates all of them simultaneously. That's the kind of thing that they were into back in the day. OK, so I hope I've tried to somewhat motivate you to be interested in constant depth circuit lower bounds. So now we're going to start in on them. And we'll start with the easy one. We'll start with depth 2. So depth 2 circuits are just CNFs and DNFs. And it's not too hard to prove lower bounds for them. CNFs and DNFs, these are concrete models of computation that we're pretty good at understanding. Still some open problems about them, though. But let's warm up with depth, showing the following. Depth 2 circuits for parity require exponential size. So in fact, we can show 2 to the n minus 1, which is exactly sharp. OK, so let's prove it. So without loss of generality, say we have a DNF. OK, I say it's without loss of generality because, well, parity is basically close under negation. It's not quite the same thing, but all the properties of parity are shared by the negation of parity. And if you negate a DNF, then by De Morgan's laws, it turns into a CNF of the exact same size. So there's not going to be any difference between DNFs and CNFs. OK, so let's say we have some DNF that's supposedly computing parity. So this is just an OR of ands. And each and feeds into the literals. And I didn't quite mention it before, but let's just say we always assume that for the gates at the lowest level, they don't feed into both a variable and its negation. That's without loss of generality because there's no need to ever do that. So in particular, the width, the fan-in down here is always at most n. OK. Good. So what I claim is that, let me add this word, computing parity. What I claim here is that every and here, I guess they're called terms in DNFs, every term or and actually must have width at least n. In other words, exactly n. Okay? You cannot have an and with width n minus 1 or less. Can somebody tell me why that is? Yeah.
You could just toggle the bit that it doesn't touch and then change, or make sure that you set all the other ends to false, and then.
Right. I was going to say true, but yeah, it's something like that. Let's see if my argument works. So let's say if let's say term t, or and t is missing either xi or potentially its negation, then set the other bits. Well, just set all the bits such that t becomes 1, and therefore parity becomes 1, because as soon as you make one term equal to 1 here, then the whole circuit outputs 1. And of course, for a given and, you can always make it 1 by setting its bits appropriately. Good, but now it's missing xi, so by, well, as you say, like toggling xi's value, well, this doesn't change the fact that t is 1. But that's a contradiction by the critical property of parity that we're going to use very much, which is that parity is sensitive to any single bit flip. Okay, this is the unique property of parity and its negation, that like whenever you change exactly one input bit's value, it always changes the output. Great, so we're almost done. So now we know that like every term has fan in exactly n. But when you have an and of fan in exactly n, that means it only accepts exactly one input. So like therefore every term accepts, outputs 1, exactly one input. Okay, but parity accepts half of the inputs. Okay, so therefore, like the circuit has to have a, at least one and per input that makes parity true. Okay. Okay, good. So great, we did depth 2, but things really start to get hard at depth 3. In fact, there's some sense actually in which the people who are like really into constant depth circuits, they have this I think correct viewpoint that really you should always like subtract 1 from the depth. Like that's like the real depth. Like they write depth d plus 1 always. Like depth 3 circuits are kind of like you should really, the real parameter is like 2 for them. And like so like depth 2 circuits are like parameter 1, which is like trivial, and like depth 1 circuits you wouldn't even think about them. So yeah, like the real action sort of starts at depth 3. Okay. So in order to prove Hastad's theorem, we actually have to introduce one more concrete model of computation, which is actually easier, simpler even than circuits. It's a very attractive model of computation, the decision tree. Okay, so decision trees are a concrete model of computation that can compute any Boolean function, but they're really, I don't want to say weak, but we can understand decision trees pretty well. They're not too complicated. So what is a decision tree? I'll just draw a picture if you haven't seen one before, and hopefully it'll be kind of clear. Okay, so a decision tree is like the representation of a Boolean function that looks maybe like this. So it has a node, which you think of querying, in this case, the bit x2. And depending on whether x2's value is 0 or 1, you follow a path. And maybe you query potentially another node. And then perhaps at that point you feel you know the value of the function, so you stop at a leaf and like output, let's say 0. Otherwise, perhaps you query another bit, and maybe you stop In some cases, let's see, let's put x3 here. Let's put a leaf here. OK, so this is an example of a decision tree. OK, so it's a syntactic representation of a function. The way it computes, in this case, on 3 bits is you just like, on a given input, x1, x2, x3, you follow like the appropriate path, and then just output the leaf value. OK, so there are, I guess, 2 main measures of complexity of these guys. One is the size, which is the number of leaves. But we're not going to talk about that all in this class, because sort of the most important parameter of all for a decision tree is the height, which is also sometimes called the depth. I'll call it h. And yeah, the height is, you can also think of a decision tree as like a query algorithm for determining f of x when like x is kind of considered unknown. So like it's a strategy for like querying the different bits, finding out what they are, and then attempting to figure out what f's value is. And so the height is like the maximum number of queries you'll ever need to make. So this, in general, decision tree computes some function, just like a circuit. I think this is the majority function on 3 bits, if I drew it correctly. And, oh, it's such a glorious picture. I feel like I don't want to delete it yet. OK. OK, so we're going to introduce this notation. dt of f, some people would write like a subscript depth here to emphasize that we're talking about depth or height, but we're always going to talk about height. It's the minimum height of any decision tree that computes f. One more technical restriction, I didn't say it here, but we always assume that like no variable appears more than once on a path. There's no reason to ever have that, so let's assume that never happens. OK, so the first thing to note is that it's always at most n. In other words, every function can be computed by some decision tree. You can just even have like a layered decision tree where you always query x1, then here you always query x2, then you always query x3. You have like depth n. After depth n, like you literally know the entire string, so you can just output the correct value. OK, and it can actually also be as low as 0 if and only if f is a constant function. OK. So turns out that decision trees are somewhat related to CNFs and DNFs via a fact I will state now. They're kind of strictly less powerful than CNFs and DNFs in a certain sense. If you have a decision tree for a function f of height at most h, that implies h has a DNF of width h. F has a DNF of width h. And it also has a CNF of width h. OK, so if you're computable by a shallow decision tree, then you're computable by a narrow CNF, and you're computable by a narrow DNF. So let me show you why this is true. OK, for DNFs, how do you convert this thing into a DNF? Well, you just look at all the leaves that are 1, and you take the OR of them. The OR of the paths that get to the leaves. OK, so take the OR of all paths, which are kind of equivalent to ands of literals, that lead to a 1-leaf. OK, and that's a DNF, and its width is at most the height of the tree. So I'll show like a disjoint DNF, like on every input, exactly that makes the thing 1, exactly one term will be 1. And for CNFs, you can do like a similar thing with like looking at the zero leaves, but like that always confuses me. CNFs are so confusing. So another way to say it is like, the decision tree depth of the negation of f is the same as the decision tree depth of f, because clearly you can just negate all the leaves. And then you can get a DNF of width at most h for negation of f, and then De Morgan's laws let you convert it to a same size and width CNF for f. OK, any questions so far? OK, so now we have two models of computation, decision trees and constant depth circuits. And we're going to kind of start to get into how Hastad and also others proved circuit lower bounds for parity. And there's a key technique. And in some ways, knowing about the technique is as important as knowing about the final results. This is a technique called random restrictions. So I'll explain that over the next few minutes. But this is an important technique not just for circuit lower bounds for AC0, but also in proof complexity. It comes up a lot. It also comes up in trying to prove lower bounds for other models like formulas and other things like that. So yeah, random restrictions is an important technique in complexity theory. So let me explain what that means. So first, let's define what is a restriction. A restriction is just a partial assignment. Okay, so it's a partial assignment. The notation that we're going to use is a mapping from the variables to either 0, 1, or star. Okay, and the 0, 1 variables are called the fixed variables. And the star variables are called the free variables. Okay, so the star variables are ones that are like remain unset. Okay, and so in that sense, it's like a partial assignment. Okay, so if you have a restriction and also a Boolean function on these n variables, you can form the restricted function, which I'll write f bar sub rho, which just basically means they'll plug in the fixed values. And you remain a function on the free variables. OK. So just as like a little example, and one reason that parity is the key function, or the most easy function to prove lower bounds by the random restriction method, parity has a very nice property that parity function under any restriction becomes parity or its negation on the remaining free variables. Okay, that's just saying if you take the parity function and plug in zeros and ones for some variables, the remaining thing is still the sum of the remaining variables mod 2, possibly plus 1. Okay, so parity is a function that behaves very nicely under any restriction. Okay, but we're actually not going to look at any restrictions. There's a second part to this technique. We're going to look at random restrictions. A random restriction is basically just what it says. So a random restriction, it's going to have a parameter, which we'll call the star probability. I'll write it as epsilon. And maybe the notation I'll use is rho is drawn from R epsilon. That means rho is a random restriction with star probability epsilon. It means for all I in n, independently, you set rho of xi, as suggested by the name, to be star with probability epsilon. OK, and the other two possibilities, with half probability each. So I guess 0 and 1 with probability 1 minus epsilon over 2 each. Okay, the most natural way to choose, I think, a random restriction. And what is the idea of random restrictions? The whole idea is sort of the following. Like, imagine you supposedly have a constant depth circuit like this one, which is supposedly computing parity. And we're going to imagine drawing a random restriction and seeing how it acts both on parity and how it acts on this circuit. So on one hand, we know how it acts on parity. It just turns the function into a parity on the free variables. We're also going to mention how it sort of syntactically operates on the circuit. So like, how does it syntactically operate on the circuit? Like if you, let's say in the random restriction fixes x1 to be 1, then like whenever x1 is feeding into an AND gate, you can just delete that wire. And whenever it's feeding into an OR gate, you can actually delete the whole OR gates because that OR gate is forced to 1. Okay, so like, and similarly, simplifications can happen when you set a variable to 0. So in some sense, a random restriction can kind of dramatically syntactically simplify a circuit. If you've set a lot, I chose epsilon for a reason here. Like in a random restriction, actually most of the variables get set to 0 or 1. So like, a lot of variables get killed, but also like it really kind of crushes parts of the circuit, and that can like propagate up, and it can really drastically simplify the circuit. And it might drastically simplify it to the point where like it'll actually become obvious that like this pathetic, remaining circuit could not be computing the still pretty complicated function parity on the remaining variables. Okay, and so then you'll say, well, that means the original circuit couldn't have been computing parity either. So the idea will be that like shallow circuits or also decision trees are very drastically crushed. Okay, let me say simplified by random restrictions. And proving this is like the bulk of the work that to sort of show that like when you set these bits, like not only do they get fixed, but like it really propagates up the simplifications and really like wipes out large chunks of the circuit. But for example, parity n isn't. I mean, to the extent that it's obviously going to be defined anymore on like epsilon times n variables, but it still remains like the equally complicated function parity, complicated, on epsilon n variables. Okay, and ultimately the strategy is going to be like show that a random restriction reduces your constant depth circuit so much that it turns into like a CNF or a DNF. And then you say, okay, but come on, we know, okay, it's no longer on the board, but like a CNF or DNF requires like full exponential size to compute parity. So that means the original constant depth circuit computing parity on all the variables must have itself had like very large size. Okay, so this is the part that we need to prove, that like shallow circuits are very drastically simplified by random restrictions. I should mention that this whole strategy was invented in 1961 by Subotovskaya, and she was studying circuit lower bounds. Well, lower bounds not for constant depth circuits, but for Boolean formulas. Okay, so no bound on the depth, but like they're formulas, so all the gates have fan out 1. And she showed that this specific property that like if you do a random restriction, it really like knocks out a lot of gates in a formula, and you can thereby show that any formula for computing parity must have size n to the 1.5. And actually, the sharp bound for how well parities can be computed by formulas is n squared, and it was subsequently proved. But her method actually is used eventually, also by Hastad, to show an explicit problem in P that requires formulas of size n cubed. And that's the best thing we know. So we actually know that for the context of formulas, there's no bound on the depth. There are explicit functions that require n cube size formulas. And that's also proved by random restriction methods. Okay. So Hastad, before that, studied the power of random restrictions in crushing constant depth circuits. In fact, CNFs and DNFs. And he proved a famous result called the switching lemma. And let me put switching in close, because when I state it, it won't be obvious like what the switch is, but I'll explain that later. And I should also put lemma in quotes because for historical reasons, I mean, he called it a lemma, but it's actually a very hard theorem. So it really should be called the switching theorem, but sometimes it's cooler to just have like your hard result be called a lemma. It's happened before. OK, so let me state his switching theorem. So let phi be a CNF or a DNF. It works equally well. Some depth to circuit. Oh, with a bound on its width. OK. And now what we're going to do is imagine drawing an epsilon random restriction and seeing what happens. This is like a syntactic object, the circuit. We're going to see syntactically how much it simplifies when you do restriction rho to it. And we're actually going to show is that it's actually, depending on the parameters, very, very likely to collapse down to a constant depth decision tree. Okay, so in fact, we'll show that the probability that the decision tree depth, the required decision tree depth to compute the restricted CNF or DNF, is super unlikely to be large. The probability that it is at least some quantity h is at most exponentially small in h. And you can put 5 epsilon w here. Okay, this is for all h, a natural number. So for example, you can select no. So let me comment on that just now. Typically, in its applications, or in many applications, we'll take epsilon to be, let's say, 1 over 10w. OK? So if you take epsilon to be 1 over 10w, that knocks out the w and the 5, and this becomes a half. So this is just 2 to the minus h. But you can take epsilon to be smaller if you want, and this is even more dramatically exponentially unlikely. It's even quite interesting to take h to be 1. Okay? When does the decision tree depth of something at least 1? It's when that thing is not constant. So you can even put a 1 here. And then it says when you do a random restriction to this CNF, the probability it doesn't even collapse to just like a constant, that's like not totally fixed, is at most 5 times epsilon times w, which is small if epsilon is like this. I'll elaborate on this in a second, but let me make one more dramatic point about this theorem, which is why it's so amazing. The dependence on the size of the CNF or DNF is not at all, which I'll give it 2 exclamation marks. So it's kind of amazing that it doesn't matter how many ores are feeding into this CNF. You can have infinitely many of them if you want. It doesn't affect the theorem. It only is controlled by the width, the maximum fan-in of these ores. Okay, and that's pretty awesome. Okay. Yeah, just going back to this typical setting of epsilon. You see, epsilon is quite small, nevertheless. I mean, in order to get some juice out of this, you have to take epsilon pretty small. In particular, right, think of this CNF as, it's a width w, so all the ores below it have at most w terms. So this actually implies that, the expected number of, remaining free variables in a fixed clause C is, equal to, or at most, 1/10. OK, so it's pretty hard random restriction. You're setting it up so that a typical term, you expect it to get 1/10 of a variable free. OK, so maybe there's a constant chance it has 1 or 2 or 3 variables free. It's probably mostly set.
What is it most of? So we have n variables, right? And
OK, so for a fixed term, so let's look at
oh, for a fixed term.
Yeah,
for
fixed floor clause.
Okay, yeah.
So this guy, good. So let's look at it, right? This guy has arbitrary fan-in. These guys have fan in at most W. This is arbitrary. So we're, fixing a lot of variables, like only such that like when you look at one of these ORs, like one specific OR, like it's probably mostly fixed. Like maybe there's like maybe there's a 10% chance or something like that it gets even 1 star. So on one hand, yeah, okay, it looks like you're crushing it pretty hard. But on the other hand, like there's a completely arbitrary number of ORs, so there could be like plenty of them with like lots of stars. I mean, it's going to happen. So it's like right on maybe the boundary, and well, we have this very powerful conclusion that like this is enough to really completely crush it down to like a constant depth decision tree. Good. As I say, but the probability that the decision tree depth of this thing is greater than h is at most 2 to the minus h in this case. Okay, let me make one more comment, which will both explain a little bit the name switching and explain like how it's going to help us prove constant depth circuit lower bounds. Okay, the point is, it shows that you start with, let's say, a width W CNF. You crush it with this random restriction rho. It turns into, you set the parameters appropriately, some depth at most h decision tree. But then this, by an observation that we erased, is also a width h DNF. It's also a width h CNF, but like let's choose DNF here. And so we've got to switch. We switch from like a width W CNF, and actually when we start doing the proof, W will end up basically being the same as h always. So we've kind of switched from a width, let's say h CNF, to a width h DNF at the expense of doing a random restriction. And why is that going to help? Well, like if you look at, okay, I've drawn it backwards here, but this is like an AND of DNFs. You can also switch the other way. So if like all of these DNFs after a random restriction switch into a CNF, then it's cool because they have ANDs up here now, and you can like merge them with this AND, thereby eliminating a layer from your circuit. And that's how the proof is going to go. You're actually going to do like a bunch of switches, basically almost one for each depth. It's going to really set a lot of variables, but it's OK because what's left is always going to be parity, which is still the same function that you're trying to prove a lower bound against. But every time you like do a switch or a random restriction, it'll collapse the depth by 1 until to the point at which you get, let's say, a CNF or a DNF. And then you're like, well, this cannot be computing parity unless it's enormous.
You can set all the variables.
Potentially. We're going to rely on the following facts, which I'm not going to bother to make 100% precise, but it's real easy. Under a random restriction, the number of remaining variables in expectation is like epsilon times n. And we're just going to presume that it's like, with high probability, right around epsilon n, which is certainly true by a Chernoff bound.
It's like after one.
Right. We'll talk about like what happens after doing one iteration. To warm you up for it, I'll tell you now, although I'll state it more carefully later. If you do a random restriction with a star probability epsilon, and then on the remaining free variables, you do a random restriction with star probability delta, it's equivalent to doing an overall random restriction with star probability epsilon times delta. It's basically the probability that you're a star after both random restrictions is epsilon times delta, and otherwise you're always like 50-50, 0 or 1. So indeed, if we do like, I don't know, 2 random restrictions in a row with parameter epsilon, it's like overall we've done a random restriction with parameter epsilon squared. So we'll be down to like epsilon squared times n variables. So in fact, let me spell that out. Yeah.
So you have 1 over t minus 1.
Pardon me?
This is why we have like 1 over t minus 1 the exponent. Because
that's right.
Like epsilon is t minus 1.
Yeah. We're actually eventually, you'll see the parameters, but we're actually going to eventually do the switching lemma d minus 2 times, but a d minus 1 will come out. You'll get the point of it in a second here. let me make this circuit now up to like level depth 5. So now there's a few more ands up here. Okay, so let's imagine that we're trying to show that, any depth 5 circuit computing parity must have very large size. It's eventually going to be, must have size 2 to the n to the 1/4. Okay, so this is now a depth 5 circuit, for example. I think 1, 2, 3, 4, 5, okay. And let's say it has size S, and let's say it computes parity on n variables. Now, we want to show that S is large. Okay, that's the goal of the proof. Let us assume, for now, okay, this is to be fixed later. Let me give us a little assumption to get us going, and we'll fix it at the very end. Let's assume that the width of our circuit let's make that into a sentence. Assume the width of C, remember this is the bottom fan-in, is at most a parameter that we'll call W, which is 20 log S. Okay? This is like an unwarranted assumption. There's no reason that you would necessarily have this. But at the very end of the lecture, I'll be like, oh, actually, it's easy to get yourself into a situation where this is achieved. Okay, so don't worry about this too much. We're going to fix it later. For example, if you want to get slightly worse parameters, you can easily achieve this by adding a dummy layer at the bottom that has fan-in 1. Now, it's certainly much less than 20 log S. You've increased the depth by 1, so that's going to hurt your parameters a little. But that's one reason to see why it's not a big deal. Eventually, we'll fix everything without losing any parameters. Okay. And in the final setting, this is going to be some power of n, like n to the 1/4 or something. OK. So what is the strategy? Let's take a look at exactly this layer. OK, at layer 2, you have many, let's say S2, but at least that's at most S, CNFs. OK, in general, maybe it's DNFs, but the arguments can be the same. So at layer 2, you have at most S CNFs. And they're all of width W. At most W. So, of course, we're going to do a random restriction on them. Let me go 2 panes over. So we're going to do a random restriction which, with foresight, I'll call rho sub 1, and star parameter epsilon, where epsilon indeed is this setting that I promised. OK. Good. So now, what do we know? It's basically written here, but for any particular layer 2 CNF, we know that the probability when you choose this random restriction that it does not simplify to a really shallow decision tree. And I'm actually just going to select H to be W here. Keep things simple. W is at most 2 to the minus W. Okay, that's literally plugging in the parameters here. But what is W? It's this. Okay, this is 1 over s to the power of 20. Okay, and this is way smaller than 1 over s, or even s2, the number of circuits, the number of CNFs at layer 2. So we can union bound over all of them. So therefore, with very high probability, by a union bound, all of these CNFs become shallow decision trees. They turn into height, at most W decision trees, and therefore width, at most W CNFs. Okay, and that's the switch. So this picture, never used colored chalk before. Let's see. Each CNF here gets switched after the random restriction to DNF. Okay, and therefore all these wires that are coming into it at lower levels can be bypassed. You just cross this guy out and put them straight into the OR up here. Okay, and that happens for all of these guys. And you basically wipe out this whole layer. Yep?
Yeah, the last line over there, you're like, all CNFs turn into with WCNFs. I think it should be CNFs.
Thank you. Yeah, that's pretty awesome that I made that mistake. It's the whole point of the proof. Great. Yeah?
Where did you write onto the right 1 over s to the
20.
20?
Yeah, this, I don't know, these numbers are not necessarily exactly picked. It's this 20 over here. This is chosen to be like much, much smaller than 1 over s.
So like here, when you're doing this stuff, like this CNFs that you have, they're kind of intersect each other.
Yes?
So then, when you transform into DNF, like, how that works? Why it's not a problem? Like,
yeah. Yeah, actually, maybe in some sense you should not think of, I said it twice, but maybe I shouldn't have. Maybe you should not think of like the syntactic operation of the restriction on the CNF, but like literally think for this CNF of what function it computes of all the variables. Under the random restriction rho, what you show is that it can be, it reduces to a function of the remaining variables, which can be computed by a shallow decision tree. In other words, a shallow DNF, a narrow DNF. And of the remaining free variables, and you can just write that DNF in here of these free variables. And that's it. Now you have a new circuit. So yeah, it also, the restriction also like kind of cuts out a bunch of variables. And the remaining variables are the only inputs for these new DNFs that show up here. So it's true that they interact, but you're like, well, that's,
so we're not doing it like for each single CNF. We're basically like erasing every scene and then constructing a new state after that.
Yeah, you're going through each CNF. After you do the random restriction, and then you're going through each CNF, and you're observing that, okay, it can be semantically, I guess, actually replaced by an equivalent DNF, computing the same function of the remaining unrestricted variables. And yeah, you put all those DNFs in there. And then you're like, oh, now I can actually cross out this layer of the circuit. Yeah?
So we could blow up the size by doing this on the circuit?
No. Okay, actually, wait a minute. By no, I mean yes. Yeah, you could. We're not going to control, that's very good. We're actually no longer going to at all try to control the size of the circuit that we have. We're going to always be controlling its width, its bottom fan-in. Very good, thank you, good point. We're only going to be controlling its width from now on, you know, as we switch. But like the parameter s that we eventually care about is like does not go away because it's like it's stuck in W to begin with. And also we're going to use, this is another thing, after we cross out this layer, what remains is, well, it's the depth 4 circuit. This is like the new layer, depth layer 4, layer 3, layer 2. We're going to be studying these DNFs and switching them to CNFs. And we are going to be using that the number of ores here is at most s. Because these guys from like the original circuit that we didn't touch yet. Okay, so if we initially said there were like S2 ands here, maybe S1 ores here, although we didn't really care, and like S3 ores here, and S4 ands here, and there's one and up here. So that who knows what the heck we did in terms of size when we replaced all these CNFs with DNFs. But it doesn't affect the fact that we still have the same number of ores as we always had at this layer. The wires are going to come in, but we're not counting wires, we're counting gates. Because, I mean, I'll write a little something, but we're going to be union bounding over all of these ores DNFs getting switched. Good point. Okay, so let's work through some more details. But yeah, so we collapse the ores at levels 2 and 3, and yeah, now we have a depth 4 in this specific case, width W circuit, computing parity or its negation on the free variables. Good. Okay, so now we're going to repeat the argument or iterate the argument. So now do a random restriction, row 2, and I'm just going to use the same epsilon on the remaining free variables. In other words, where row 1 had stars. And I said this before, but it's important to repeat it. Kind of the combination of row 2 and row 1 is itself a restriction. And it's distributed as a random restriction with parameter epsilon squared. Okay, because the probability of a variable lasting both restrictions unset is epsilon squared, and everything else gets set to 0, 1 independently with probability 1/2. Okay, so the argument is exactly like before. I'm going to put the argument in a random order on the board. So once more, union bounding over these S3, which is at most the original S DNFs. With very high probability, they all switch to CNFs of width W after row 2. Okay, and then you can collapse another layer. Okay, and we're down to depth 3. And we're going to do it one more time. So as I mentioned before, we're going to keep doing this till we get to depth 2. So once more, row 3. So overall, our big restriction row, which is like row 1 followed by row 2 followed by row 3. It's distributed as r epsilon cubed. And we get down to a width W, depth 2 circuit, in this case a DNF. Okay, so in general, we're going to do d minus 2 random restrictions. Okay, and so depth, the initial depth d will go down to depth 2, and width w. And the restriction rho is going to be distributed as a random restriction with parameter epsilon to the d minus 2. Okay, now we stop. And the depth 2 circuit is computing parity or its negation on about epsilon to the d minus 2 n variables. Okay, again, this is with high probability. I mean, if you're being really careful, you have to worry about this too, but the number of remaining variables after an epsilon random restriction is very concentrated around epsilon times the number of variables you start with. So you can do a little Chernoff bound, or probably even Chebyshev is enough to take care of that. Or you can also prove the switching lemma where you always put in exactly epsilon n stars instead of a random number of stars with expectation epsilon n. It's actually about equally easy to prove. Good. Great, but now remember, one of the first things we proved is that like any depth 2 circuit computing parity must have width that's at least the number of variables. Okay, so therefore, with high probability, we get into a situation where W, this width, has to be at least epsilon to the d minus 2 times n. Okay, I'll put a little twiddle there. Maybe you lose some tiny factor. Good. But recall what epsilon is. I think it's no longer written, but recall epsilon was 1 over 10w. So this is equivalent to w being greater than or equal to up to a constant factor, 1 over w to the d minus 2 times n. Okay, and now we rearrange. So w to the d minus 1 is omega of n. And now finally remember what w is. Up to a constant factor, it's log s. So shall I write it here? I guess so. Order log s to the d minus 1 is omega of n. And then I'll just put the d minus 1 over here. So it's to the 1 over d minus 1. Okay, and that's finally what we want to prove. If we exponentiate this, we get that s is at least exponential in n to the 1 over d minus 1. Any questions? Okay, so how exactly the numbers play out at the end. It's maybe not instantly intuitively obvious, but you do this calculation, and that's how it goes. I suppose actually, except for one thing, which is this. So I mean, the final numbers depended on seemingly this starting point. It's 20 log s. So why is this the starting point? Okay, so the last thing I'll do to really complete the proof, I should put this in quotes because we're not really done, is fix this assumption. And to fix that assumption, okay, we're faced with this situation at the beginning. Well, actually, the bottom fan-in could be anything. It could be n. I mean, what do you know? So how do we get into a situation where the bottom fan-in is a lot less than n? Well, we do one more random restriction. In fact, we do a random restriction at the very start to crush the fan-in at the bottom level. So now it's later, and we're fixing this assumption about w. Okay, so actually our initial circuit could have any fan in. But we just start everything with a random restriction rho 0 with star probability 1 over 100. Okay, now let's see. First of all, this won't affect really what's going on, the calculations at the end. Right, so if we throw this in there, okay, so this final random restriction, instead of having parameter epsilon to the d minus 2, it'll have parameter like 1 over 100 to the, times epsilon to the d minus 2. But anyway, like I wasn't worrying about the constants all the way through, so it'll just change the final constant in the omega here. But it'll have the good property of like cleaning up in some sense the potential large fan-in at the bottom. So consider the ors at the bottom layer. Okay, or they could be ands, but the argument is going to be the same. The point is that if under rho 0, any of them gets a 1, well then it's killed. I mean, if an OR under this random restriction rho 0 gets like a 1 feeding into it, then that OR is definitely satisfied, and you can just like erase it from the whole circuit. And similarly, ands are killed by zeros. And for a fixed, OR, it's very likely to get a 1 if it has large fan-in, because like you pretty much have a 1 like half the time in a random restriction. I guess it's maybe 0.495 or something of the time with this star probability. But the probability that a given OR gets no 1s is exactly 1 plus 1 over 100 over 2. This is the probability that it gets a 0 or a star to its width. Okay, I'll finally erase this. And this is, much less than 1 over s if its width is greater than w, which is 20 log s. Okay, this is basically a half, and then half to the power of 20 log s is again 1 over s to the 20 or so. Okay, and so you can union bound overall the bottom layer gates and get this very high probability. All ORs at the bottom layer with width greater than w get killed. Okay, and then you can start the rest of the proof. Okay, so that's the real end of the proof. Okay, any questions about that? Good. Great, well, it feels like we're done, but there's one key thing which we missed, which was proving the switching lemma. Yep?
I missed this earlier, but are we assuming that like all the NOT gates are pushed to the bottom?
Yeah, the very, very, very first step is push all the NOT gates to the bottom. Okay. That could increase the size by a factor of 2.
How does that happen?
What's that?
Do you have an answer to the question, how does that happen?
How does what happen?
I don't know, like this whole proof, it just, I don't know, like, no, yeah, it seems like magic, I have nothing to say more, it just seems like, yeah, it works, but.
Yeah, I mean, I guess, I don't know, I can only like repeat some things that I said, which is the observation that, well, just Boolean circuits simplify even more than is obvious when you do a random restriction. I mean, it's obvious that they go down to epsilon times n variables, but they simplify like even more than that. because of this effect that like, if you stick a 1 into an OR, it gets killed. And if you stick a 0 into an AND, it gets killed. And in some sense, that's it. I mean, like, imagine the switching lemma had just told you that when you do a random restriction, it's very likely that the CNF or DNF turns into a constant. It does actually tell you that if you set the parameters like strong enough. I mean, if you try to set them to that strong, then like it's not going to overall work. But like, imagine that something like that was true. And that's a property of CNFs and DNFs. They're depth 2, right? So like maybe it's quite plausible that they get crushed by a random restriction because like you just need like for a DNF like one AND at the bottom to turn into a 1, and the whole thing is crushed, or like everything to get set. So maybe it's like plausible that like with a very powerful epsilon random restriction, epsilon being quite small, like you can just wipe out the whole bottom layer or bottom 2 layers of a constant depth circuit. Okay, now you have to do this like constantly many times to like wipe out the whole circuit in some sense. And you can see that constant many times is costing you a lot, right? Because your epsilon random restriction, which is maybe already taking your number of variables from n down to n to the 0.1 or something, it's going to turn it into an epsilon to the d. So you can really only afford to do that like very few times before you just wiping out your original hard function parity just by killing all its variables. So there's some kind of trade-off there, and maybe you can slightly see that like you can pull something off for constant depth circuits if you can prove a strong enough statement about how CNFs and DNFs get crushed by random restrictions. Okay, so as I said, we're not going to prove the switching lemma in the next 2 minutes. It's quite a hard theorem, actually. It takes maybe an hour to prove. It's in the textbook if you want to read it. Let me tell you just before we go about different proofs of the switching lemma. So Hastad's proof originally, very clever. It's an induction, and it's got a crazy move in it, which is that you prove that not only do you switch with high probability when you choose a random restriction, but it remains true if you condition on like almost an arbitrary event, which is kind of amazing. You need to like do this in order to carry out an inductive argument. So it's like the power of like strengthening the induction hypothesis. It's quite amazing, a little bit hard to read. Subsequent to that, like Razborov wanted to use the switching lemma in the context of proof complexity. And in their context, he had to show, for his own reasons, that there was like a very simple, in some sense, proof of the switching lemma. And like Hastad's proof was not that simple. So he had to kind of like redo the proof. And he redid the proof in a very interesting way. It like uses this strategy where like you want to show the probability of something is small. So you want to show that the number of like bad outcomes is small. And you do that by like encoding each outcome by like some kind of object. And then you show like you can count the number of objects space to show that that's small. And therefore the probability of the bad events is small. It's a very interesting argument. It's written down more clearly by Paul Beam. And that's the proof that you'll usually see in like textbooks and stuff. That's the proof that's given here. I'm going to be not here next week. I'm at a conference. So in lieu of lectures, I'm going to make some videos. And one of them, I'm going to try to actually do Hastad's original proof. Because it's actually, despite its reputation, it's really no more complicated. But like nobody ever like talks about it. So I'm going to try to talk about it. And finally, I may also mention, 1 year ago, these people, Tony Patassi and Ben Rossman, Rocco Servideo, Li Young Tan, they were also doing some work in complexity theory where they had to prove a switching lemma about a different kind of random restrictions that like restricted the function space to like a vector subspace. And like it was such a complicated random restriction that they're like, man, there's no way we're going to be able to prove anything about this using either Hastad or Razborov's complicated proof. So they invented a new kind of switching lemma, which is quantitatively weaker, but easier to prove. So hopefully I'll also prove that, or show you a proof of that as well. It only gives you lower bounds of size n to the log n for computing parity, which is much worse than exponential, but it's easier to prove. OK, so we'll stop there. Next week I'm gone, so nobody come to class on Tuesday or Thursday, including the filming people. But stay tuned because I'll make some videos instead.